we're going to go with question 3.6. Given refrigerant 134A vapor at 0.8 megapascals and 80 degrees Celsius, determine the specific volume using thermodynamic tables, the ideal gas equation, and the compressibility chart. So just to familiarize ourselves a bit more with all three. So let's do this one. No, I don't want that, sorry. There we go, 0.8 and 80. I was just trying to figure that out. So we're at 0.8 megapascals and 80 degrees Celsius, which of course corresponds to plus 273 in Kelvin. So 353 Kelvin. Okay, now from thermodynamic property tables, it's pretty simple. We're just reading it off. So all we have to do is go to the tables. And I'm going to just start by guessing it's in the superheated vapor tables. So 0.8 megapascals here, okay. 80 degrees Celsius, okay. And we're looking for the specific volume, which is the first column. We can just check here. Yep, it's the first column. So we see the specific volume at 0.03264. So let's write that down here. And of course, it's meters cubed per kilogram. So that's as simple as that gets. It's using the thermodynamic property tables. So the next way we're going to do it is we're going to use the ideal gas law, right? So ideal gas law, we have pressure times volume equals, sorry, well, I'll do it a different way. Pressure equals density, R, which is which depends on the material, and T. Okay, and we know again that rho is 1 over specific volume. So pressure equals RT over specific volume. So naturally, specific volume is equal to RT over P. Now R, we can, T and P, we know they're given, right? They're given right over here. But R we have to get from the charts. So if we go all the way to the top, and we look in this column here for refrigerant 134A, we see that R is 0.08149 kilojoules per kilogram. So 0.08149, I'm just going to keep that written down there. Okay, but of course, converting it into joules per kilogram, we're going to use that in this equation to keep the units consistent. So V equals R, which is 81.49 if you multiply by 1,000. T is 353. Make sure you use Kelvin and not the 80 degrees Celsius. And the pressure is 0.8 times 10 to the 6. And if we do all that on the calculator, we should get 0.03596 meters cubed per kilogram. So comparing these two values so far, see the ideal gas law sort of overestimates it a little bit, but it's not terribly off. 0.32 to 0.35, more like 0.33 to 0.36 if you round it up. Okay, but that's how you would do it using the ideal gas law. And now we're going to do it using the compressibility charts. So compressibility charts, remember, we're going to think about it in terms of reduced quantities. So reduced temperature, reduced pressure we can start with. So reduced temperature, we know is our temperature that we have divided by the critical temperature. Well, I don't know the critical temperature by heart, so I'm going to go get it from this column over here. And if I go to R134A, I see it's 374.3. So 3 74.3. And since this value is getting very close to 1, we can see that we're going to have problems if we use the ideal gas law. And this value is indeed very close to 1. It's 0.94. Okay, and similarly, we can get the reduced pressure, which again is our own measured pressure divided by the critical pressure, read off the same chart. It's this one here, 4.067 megapascals. 4.067. So 0.8 divided by 4.067, and we see that our pressure is 0.19, well, actually it rounds up to 0.2, okay? Okay. So we're going to use these two values over here, 0.94 and 0.2, to find our reduced specific volume. And from the reduced specific volume, well, actually, it's faster if we get the compressibility factor Z, but we'll see how we do that in a second. So let's go here, all the way here. So we had 0.94 for the reduced temperature, okay, which is almost on this solid pink line here, right? It's close to 1. And then we had 0.2 as our reduced pressure, which is about here, somewhere on this line. All right. So if we see where the two intersect, we can see they intersect right around here. So we have a Z value of about 0.92. So Z equals 0.92. Now, if we take that Z equals 0.92 and we use this equation, we can just solve for the specific volume. So isolating right away for the specific volume, we have V equals ZRT over P. Okay, so that means V equals 0.92. R we can get, sorry, it's actually in the same thing. We can get from here, this column here, we can get R. For refrigerant 134.8, we already got R before, excuse me. So it's 81.49. Sorry, there we go. 81.49, and the temperature we said was 353. All of this divided by the pressure of 0.8 times 10 to the 6. And if we calculate this, we should get 0.0331 meters cubed per kilogram. Let's just compare that to the others. So 32, 35, 33. So they're all more or less in the same range. But this is how they compare. And that's how you do that.